Hello everybody, it's Mr. Ray with our next lesson in grade 12 calculus. We are in our derivatives unit, and we're going to learn about how to sketch derivative functions if we know the graph of the original function. So the important thing to remember about derivative functions is they're actually measuring the slope of the tangent as you go through the original function. So just remember derivative and the slope of the tangent and instantaneous rate of change. Those are exactly the same thing. We just have different names for them depending on the situation, but it's all measuring the same thing. Okay, so what we're going to do today, it's a very quick lesson. I've got a graph of a function here, and what we're going to do is we're going to, on top of this graph, we're going to put the graph of the derivative. So there's some new concepts to learn about, some tips on sort of the steps you should take when you do this, because it might seem a little overwhelming at first, but a few key things to remember. Now we're going to learn about one important new thing called a point of inflection, which is a point on a graph where the slope of the tangent changes from increasing to decreasing or from decreasing to increasing. So it's a change point. It's a point of inflection, hence the name. And we will be looking at how to find those on a graph and what's the importance of the inflection point when it comes to graphing or sketching the derivative of your original graph. Okay, so what we're going to do, these first four points here are really the steps you would take. This last one is kind of more of a tip, and so I'll talk about that first, even though it's the last thing mentioned. And it's a good idea to think about this process using either a pencil or a straight edge. So I have my handy see-through transparent ruler here. So I want to let's talk about, you could actually use this or a pencil or anything straight to sort of determine what point am I going to be graphing to illustrate what the derivative of this function is at a given point. So we're basically going to kind of almost go along this curve, little mini steps at a time. We're going to have this ruler that's going to represent the tangent. So this edge here is the tangent. Say when we start here, if I was to approximate what I think the tangent is, it would probably be this. So in terms of the slope of this line, I'm not expecting everybody to be experts on just looking at this and saying a whole lot about the slope, but the key thing is that it's a negative slope. It's going down to the right. So this the derivative of this point will be negative because the slope at that point is negative. And as we kind of go around the bend here, you can see as I'm moving along this line, my tangent is changing all the time. So you can see the tangent is getting less and less steep. It's still negative because it's going down to the right, but the actual value of the slope is increasing. It's going from fairly highly negative to medium negative to about right here where it's about -1. And as we get to this point at the bottom, you can see it's getting flatter and flatter, still negative in terms of the slope of the tangent. But we get down to the bottom here, and you can see the slope of the tangent at this minimum is a horizontal line, and the slope of any horizontal line is 0. So in terms of what's happening as we go around here, it was fairly highly negative here, increasing to the point where it gets to 0. And then as we continue, you can see as we turn the corner there, the slope has changed from being 0 to being positive, very low value, very low positive value for the slope. But as we keep going, you can see the slope is continuing to increase and still more and more positive as we go up. And then we get to about that point there, 0, 0. And you can see At that point there, from here to here, the slope was increasing. But as soon as we hit that point, you can see the slope starts to decrease at that point. It's still positive all the way along here because, well, from the time we stop being horizontal all the way up here, and you can see it's getting less and less steep. So the slope is actually decreasing, but still positive. And as you get to the top, just like when we got to the minimum, the slope becomes 0 here. Okay, so, and you can kind of continue the same thing as you go down. So the slope is 0 there, and now it starts being negative again, more and more negative, more and more negative, to the point where it gets down to here, and then it starts becoming less and less negative. And then it gets to the bottom, and the slope is 0 again. Okay, so we actually encountered 2 points of inflection as we went. These 2 points right here are points of inflection. Hopefully you heard me say, as you come up here, the slope is increasing up till this point, and beyond this point the slope is decreasing. And that's the definition of a point of inflection, when the slope changes from increasing to decreasing. Okay, so that's important to understand. Okay, so let's go back and let's actually, now that we've kind of done this journey of the slope of the tangent as we move along this curve, let's start building our derivative graph for this function. Okay, so we always start with probably the easier part, and that's we look for when we have max or min values, and those are like local minimums or maximums of the graph, and we can see we've got two minimums here and a maximum. So at that point, you can see, if you remember, all 3 of those points had a slope of 0. Okay, so the very first thing we do is we look for those max or min values where the slope is changing from negative to positive or positive to negative, and those values, those x values where that happens, it's going to have a slope of 0. So the slope of the tangent is 0, but therefore the derivative is 0. So let me do this in green so you can see the difference. Okay, so we have our first point of our derivative function, and that's where the original function had a minimum, and now that we have a maximum here. So if I use that same x value, that the derivative function will have a value of 0 because the slope of the tangent there is 0, and same reasoning for this point here. That point, that x value has the derivative function at that value is 0. So we have 3 values of zeros for the derivative function that always occur at the minimums and maximums of the original function. Okay, so we've handled those. Now we go back to those 2 points of inflection that we spoke about. Now, the points of inflection create max or mins of the derivative function. Okay, so if you think about this point of inflection here, remember the slope of the tangent was increasing, and at this point it starts to decrease as we go along the upper part here. So where would the maximum, where would be the highest slope, would be right at this point here, at this x value of, I guess that would be 0. So the maximum, I'm going to have a maximum for this derivative function at x equals 0. Now I'm going to put it there for now. And so how do I know what the actual y value is here? It's pretty easy to tell what 0 is, but how do I know where this maximum should occur? Well, I'm kind of, if I was to, if I was to put my slope of the tangent there, if I was to guess what that slope was, I'd say it's more than 1, but maybe less than 2. So I put it right about there. Now, that's the thing about what we're doing here. Notice the verb sketch. Okay, sketch means you're going to capture the key features of this graph of the derivative function, but it's not going to be 100% correct. And we don't expect it to be, but we want to have certain aspects of it are very correct. But in terms of some of the y values here, you're not expected to actually calculate the slope of the tangent at that point. Let's give it our best estimate. Okay, for sure it's positive, and it's the highest positive value there is anywhere on this function. That's the steepest positive slope there is. So that's going to be a maximum. Okay, if I looked at this other point of inflection, remember the slope of the tangent as we go down here. Okay, 0, slope is 0, slightly negative, more negative, getting more and more negative, increasingly negative until it gets right to that point, and then it starts to, the slopes of the tangent starts to increase again. It's decreasing all the way down here, and now it starts increasing. Because increasing meaning getting less negative and more towards 0. Okay, so at that point, what could we say about the slope of the tangent there? Well, that's as steep a negative slope as there is on this graph. That's extremely steep, but it is a negative slope, so I'm going to have a negative value, but it's going to be the most negative value that the derivative has. So I'm going to say it's about the same as this value, but obviously negative this time. So I'm going to plot my point right about, let's go right here. And again, sketching, it's not going to be perfect. Okay, so we've handled the points of inflection. We haven't joined anything yet. We're still going to think about how this works. Now, the next part is we're looking at where the original function is increasing. So where the original function is increasing means you're going to have areas of the graph where f of x is increasing create a positive value for f of x. So where is this slope increasing? Well, the slope is increasing from here to here. It's increasing from here to here. Actually all the way up to here. So from here to here, the x values from there to there, I have a positive slope, so therefore my derivative graph will have positive values. And that kind of makes sense based on what I have here. I have two values here that are 0, and a value that's about halfway between, which is positive. And that kind of lines up with what I just said here. So between these two x values, we have a positive slope, so therefore our derivative graph should be above 0. Okay, so I'm actually going to fill that in. And again, don't expect perfection, but so that's basically saying between here and here, I have a positive slope, so therefore my derivative is positive. Okay, and it ends at the two places where my slope of the tangent is 0. So to the left of this and to the right of this, I'm going to have a negative derivative because the slope is negative. Okay, and then I could also look at the fourth part here. Well, where else is it increasing? Well, it's increasing again from this point here to this point here. Okay, so I could maybe fill in here because this probably is a point of inflection as well, but we don't really see what's going on. So it's kind of replicating this part of the graph over here. So I'm going to take my best guess and say that that's what that derivative graph would look like there. Now I go back to the last part. Wherever the slope of the tangent is negative, I'm going to have values below. I'm going to have negative values for my derivative. So, for example, from here to here, you can see that I have a negative slope here. So therefore my derivative will be negative from here to here. So something like this. It's going to be most negative there, which looks again like another point of inflection if it was to continue. So it has approximately the same value as as this one does. So, and then over here, from this point on the graph to this point, you can see the slope is decreasing. I have a negative slope. So from here to here, so from this x value to this x value, I have a negative slope, so therefore my derivative is also negative. So I'm going to fill this part in here. Okay, and that's a fairly accurate sketch of what the derivative function looks like. Okay, so the most important thing for you to practice is this handout I have here. I basically have, I believe it's something like 12 graphs of functions. So what I'd like you to do is try to come up with what you think the derivative function looks like. And then on the second page is are the graphs of the derivatives. So you can kind of find the one that you just drew, hopefully, and that's going to match up with the original function from the first page. So it's like a matching exercise, but you kind of have to create your own derivative graph first and then go find that on the second page and match it up. Okay, so there's also a single question from the textbook for you to do as well, but this should give you a good exercise on thinking about, okay, if this is the graph of my original function, what would the graph of the derivative look like? So there's some key points. The max and mins will always create a derivative value of 0, and wherever I have a point of inflection, that's where I'm going to find my max and mins of the derivative function. And then you also look at where is the slope of the original graph positive, and where is it negative, and that's going to tell me whether my derivative is above the x-axis or below the x-axis. So hopefully that gets you going. In our next few lessons, we're going to be looking at the actual tools and techniques that we use to take derivatives of all sorts of functions, equations of functions. So that's a very important part of the course. So we'll get to that. We look at the power function, we look at polynomials, and get more and more complex as we go along. Okay, so until the next lesson, have a good day, and see you then.